In the video, we can see two persons with different knowledge levels approaching the same questions. And ironically, the person with the less knowledge, the fourth grader, provided a much better, a much cleaner solution than the person who knew calculus. Well, by the video, it's obvious that the kid outsmarted the person, but I feel like the video does not justify how genius the solution really is. So let us analyze and understand what had actually happened in that video. We have this integral. Now person 1 had this thought process that if we can factorize it, then we can implement integration by partial fractions. But he had quickly recognized that this is going to be very tedious, very algebraic, like very demanding, and then he had skipped over to this method by the Taylor expansion of the binomial theorem. But let us understand what was his thought process and how he actually got the answer, and let us see what are the other ways that we can possibly solve this question with. Once we understand what had actually happened and why this question is so hard, then only will be able to truly justify, truly celebrate the genius of the kid's solution. Now let us take x raised to the power 5 plus 1 as polynomial. Now the solution, we have to factorize this. So let factorize this into non-factorizable parts so as to imply integration by partial fractions. If we take this, the solution is obviously minus 1. Minus 1 raised to the power odd is minus 1. Minus 1 plus 1 is 0. So x is equal to minus 1 is a solution. So x plus 1 is a factor. Coming over here, x plus 1 is a factor. We will divide the polynomial by x plus 1 so as to obtain this polynomial of fourth power. When we get this 4 power polynomial, we can take it to be the product of two polynomials. We can take it to be the product of a cubic with a linear or two quadratic. Now we will just take this condition and we will reject this condition because, well, firstly we have to break down the cubic again into quadratic, and we don't know the quadratic formula. We know the quadratic formula, but we can't actually employ it. The cubic, we can apply the quadratic formula very easily. That is very simple. So let us take this polynomial equal to this quadratic into this quadratic with the coefficient of x being a and b respectively. We have not taken other variables because the coefficients of x greatest power is 1 and the smallest power is also 1. So we only need two variables a and b. We multiply this, we get this term, and then if we simplify this, we get this polynomial. Comparing the coefficients, a plus b is equal to minus 1, a plus b plus 2 is plus 1, and again a plus b is equal to minus 1. So we get two variables and two equations. We can get the values. Now we get this system of equation. A plus b is minus 1 and a into b is also minus 1. From 1 we will get the value of b and put that value of b into 2. We get this quadratic equation. Now applying the quadratic formula, we get a is equal to minus 1 plus minus root 5 by 2. Depending on what case we take, if we take a to be plus part, then b becomes the negative part. If we take the a to be negative root 5 part, a becomes this and b becomes this. So this is equivalent cases. Just the value of a and b flips because the quadratic itself were identical. So these are just identical, these are equivalent cases. But here is one other thing, if we take minus 1 common from this, would it not become 1 plus root 5 by 2, right? But recall 1 plus root 5 by 2 is a very special number, it is the golden ratio. Now for those who don't know what is the golden ratio, it's a mathematical constant that has the value 1.618 approximately. It is present in every beautiful thing, from our face structure to the proportions of our body parts, to how a flower blooms, or how a seashell is formed, how the stars are, how the gaseous clouds, nebulas. Basically, everything in nature follows this pattern, the golden ratio. The pages we use, A4, A3, they are in the golden ratios. The golden ratio can be obtained by the Fibonacci spiral, and the Fibonacci spiral is frequently used by designers, artisans, producers, photographers, cinematographers, such a way that the elements that we want to focus are arranged in the golden spiral. We design a movie poster in this way, we can make a photograph in this way, because the golden ratio is very natural, it is very pleasing and soothing to the eye, hence it's a very beautiful number and it is associated with beauty. But that's another story. 1 plus root 5 by 2 is 5, but that is not actually required here, just the a and b becomes in term of 5. Now we get, finally we factorize x to the power 5 plus 1 into this. Okay, now we can just take LCM, simplify this, it becomes this. X plus 5 is x to the power 5 plus 1 is this. uh, Take a reciprocal, we get this. Now we can integrate using partial fractions. We have linear multiplied by quadratic multiplied by quadratic. We can easily use partial fractions here, but it's going to be very tedious. The result is that we are going to get this. Now we have to apply the formula that we know, integration x square minus a square dx is 1 upon a tan inverse x by a plus some constant c. But you know, this is going to be very complex, it's going to be very tedious, very hard to do by hand. So rightfully the main character had decided to drop this method and jump over to binomial theorem's Taylor expansion. Recall what was binomial theorem? This is wait, more correctly, this is a binomial, a plus b. A can be anything, b can be anything, raised to the power x, where x is a natural number. We know binomial theorem as this. I have just written it in sigma notation, but we have only studied the binomial for x belongs to natural number. We haven't studied the formula for half, zero point 0.5, minus 1, minus 2, only the natural numbers. So, but we can get the formula of the binomial theorem for any arbitrary x using the Taylor's expansion. And okay, now what is the Taylor's expansion? Basically, Taylor was a mathematician who had devised how to break down complex formulas into simple polynomials. We want to integrate, we want to differentiate, or we just want to study and analyze some functions. The functions going to be complex, right? But complex functions are very hard to integrate for our solution, for our question. Integration of this is very hard, but if we can get it into simple x to the power 3 plus x to the power 5 plus x to the power 7 in such a term, in simple polynomials, we can distribute the integral and we can simply apply a formula. X to the power n integral is x to the power n plus 1 divided by x n plus 1. We can apply that formula very easily. So the Taylor's expansion is that if we want to find the expansion of a function, all we need to do is we have to differentiate it at a value a, multiply it by x minus a, and divide it by the index is factorial. We got to repeat, rinse and repeat this process from 1 2 3 4 5 6 till infinity. We will make flukes. Basically all we are doing is flukes. We are approximately getting closer to the function, closer and closer, and when we do this infinite times, we will get exactly the functions in the term, expanded term of simple quadratics. Now all Maclaurin did was put a is equal to 0, and voila, we get the Maclaurin formula, which is very easier to use, but let's approximate less exact for x which deviate from 0. So this is the expanded form of Maclaurin's formula, but that's in another story. All we need to know that this binomial theorem can be expanded from the Maclaurin's expansion as this. Differentiate it once, multiply it by n, then differentiate once again, then multiply it by x squared and divide it by 2 factorial. Differentiate it again and multiply it by x cubed divided by 3 factorial. Do this infinite times and you will get the expansion of x plus 1 raised to the power n for any arbitrary term. Binomial theorem for any arbitrary term is this form. Now put n is equal to minus 1 because we had this, right? We had this. So we can just put it x raised to the power 5 plus 1 raised to the power minus 1. We basically inverse is just to the power minus 1, right? So for any x plus 1 raised to the power n, we get this. Now isn't this a GP with the common ratio minus x? Just put here x as x raised to the power 5 because that was what we actually needed. If we put that, it will become 1 minus x raised to the power 5 into 1 plus x squared, that is x to the power 10, 15, 20, what? 20, 25. Yep, we obtained this. Now the GP is formed, and luckily because the integral's bound was from 0.2 and minus 0.2, and obviously 0.2 is lesser than 1 and minus 1 respectively. No, they are lesser than 1, so we can use the formula of the sum of the GP for x is smaller than 1, which will yield us this, or we can just integrate this. We can integrate this. We can distribute the integral and we can just apply the formula x raised to the power plus 1 divided by the plus 1 part, x power 5 plus 1, that's 6, x raised to the power 6 by 6, x raised to the power 11 by 11, 16 by 16, 21 by 21. We will get this, and x raised to the power 0 plus 1, that's 1, x raised to the power 1 by 1, that's just x, from 0.2 to minus 0.2 to 0.2. Now we know that 0.2 is a very small number, and small number is the power big is extremely small. For example, just take 0.2 raised to the power 3. It's small, yes. 0. Let's take the second term as a matter of fact. It will yield us this. The third term itself becomes this. So you can imagine how quickly these values are approaching 0, and moreover, to make the matters worse, this is minus, this is plus, this is minus, so these actually cancel out each other, and at last a very small value is obtained. Even though 0.2 itself is small, the value is gonna be even smaller, so small we can approximately put it equal to 0. So these are just going to vanish, and all that's gonna be left is x from minus 0.2 to 0.2. We put the value, we get 0.4. This is how the main character was actually able to get his answer 0.4. Now there are other solutions to this problem, we can use complex geometry. Now note, after this point I don't know what is actually going on. I don't know the concepts behind these. Before this point I was able to explain and handwrite all this because I knew what was going on. I was able to explain it, I knew the concepts. But now I don't know what exactly is going on. I have a slight idea. I know what is the complex geometry. I know this is a circle. I know how to make a line in the complex geometry, but I don't know what we are actually doing with these. So using complex geometry, assume you can read this. Assume a line from the limits on the real axis, 0 to positive real axis, an arc, a circle which is only this arc, a line to the original parameterized by say exp 2 pi I by n into t. I don't know what is going on and I don't know how it is going to yield us the answer, but it does yield us the answer. Then we have the gamma function. The gamma function, what it does is basically we have studied factorials, right? We have studied factorials, but we have only studied factorials for positive integers. We have only studied for 0, 1, 2, 3, 4, 5, 6. But in factorials exist for all real numbers except negative integers. Minus 1, minus 2 don't exist. Minus 1 factorial, minus 2 factorial don't exist, but minus 1.5 factorial does exist. So gamma 0.5 I'm just going to give you an example, is root pi, which sounds bizarre. How do you arrange half objects? The number of ways you can arrange half objects is root pi. It sounds bizarre, but because these are not integers, these are not natural numbers, so don't make this analogy from the permutation combinations. That's a different story, but gamma z can be written as the integral 0 to infinity t raised to the power z minus 1 e minus 1 dt. If we solve this integral, we will get the solution. I don't know how we get the solution, but we get the solution. Now we also know that 1 divided by 1 plus x to the power minus 1, same thing, positive n minus n positive n will yield us 1. Using that we will obtain this. We just transport this minus 1 here, right? Then we will get this. We integrate both sides. For something x that's lesser than 0, we can apply the formula of GP again here. We can apply the formula of GP. We will get this. Now just sum it and you will get the answer. But if x is greater than 1, we can't apply GP. We have to use this. Now this is just one thing. There are two sigmas here. Sigma 1, sigma 2 and a constant. You can see how complex it gets, how ridiculously hard it gets. And you gotta do it in sigma. You gotta find the terms and you are gonna add them. There are many other ways. There's Chepkie's theorem, there's Robert Israel's method, there's Lesch-Phi function, there's a hypergeometric function. I don't know what these are. I know that these yield us the answer to the question. Now we have studied how demanding this question is, what all we have to do so as to get the answer. Now you might sense it, why this question actually is so hard, and if we can get an easy method, why it would be so genius. Now we have already, now if we plot the function itself, we will get this graph. Now we can approximately sense this, it's just a straight line. Well, it's not a straight line because it's x to the power 5, and we have already discussed for bigger power, and when x is small it gets negligible when the power is big, and 5 power is quite big. 0.2, this is going to be approaching very close to small 0, and because it from 0 minus 0.2, 0.2 is already small, its square is 0.04 and its cube is 0.0008. It is going to be very small. and when x to the power 5, it's going to be very very small, 0.000 something. So we can, in this range, every value is 0. For every value we can just say it's 1 over 1 plus 0, x to the power 5. In this entire range is just 0, so the function just returns 1. So the function is a constant function in this range. But if the function returns 1 always, by the definition of function, the answer returned by the function is just the y coordinate. So the y coordinate is always just 1. This is 1. This line represents y is equal to 1. So we can see this length is just 0.2 into 2, that's 0.4. And what is the integration? It's just area under the graph, but this is just a rectangle, so 1 into 0.4, length into breadth, length into height, we will get 0.4. This is why the solution was so genius. All it took was to make the graph, to understand that for very small values it's just going to be acting as a constant. And all I wanted to say why I did this is to highlight that this is the beauty of maths. You may learn new concepts, tools, you may learn new techniques and algorithms so as to apply those tools, but the beauty lies in its inherent harmony. You could use integration, or the golden ratio, or the gamma function, or you could use the Taylor's expansion. You could use all these higher level terms and methods to get the answer, yet you will stumble upon the same answer. There is no one correct method to approach a problem. No hard and fast algorithm exists in mathematics. Mathematics just rewards those who think out of the box, those who seek unconventional methods. Mathematics rewards those. It is not to be confused with the duel of knowledge, but mathematics is just a test of intellect. When such seemingly complex problems have such intuitive solutions, you cannot help but scream Eureka. If you look at the impossible problem and you are confused, you are clueless how to approach this problem, this is very complex. And when you glance at the solution and it's so simple, then you will feel dumb because the approach is so simple. And at that point, because you have realized how hard the question was otherwise and so simple the solution is, you are going to praise the genius that the solution provider has. You cannot help yourself bow in respect and admiration for the bizarre yet beautiful ocean of creativity, of intelligence that mathematics is.